Hello everyone, I am Rahatu Rabbi. I am excited to present our paper Contrast Then Confidence, Contrastive Retraining for Uncertainty Aware Out of Distribution Detection in Satellite Imagery. Let's start with the core problem. The reliable deployment of Earth observation or EO image classifiers is absolutely essential. We rely on the systems for high-stake applications like environmental monitoring, agricultural field prediction, and disaster response. However, real-world EO systems face a major challenge. The data they see in deployment rarely perfectly matches the data they were trained on. Satellites encounter what we call out of distribution or OOD inputs every day. This can be caused by seasonal changes, geographic diversity, or even variations between sensors. The dangerous part isn't just that the model get confused by the OOD data, it's that they fail confidently. A model might look at an unfamiliar landscape and predict it is a forest with 99% confidence. Well, to improve robustness, the research community has largely explored two separate avenues. Self-supervised representation learning to improve how well models generalize to new data, and Bayesian uncertainty estimation to help models quantify when they're unsure. But here is the gap. These two approaches are almost exclusively investigated in isolation. We don't fully understand their combined potential across different model architecture. Many existing methods require massive amounts of data to achieve reliable OOD detection. Our objective was to fix this. We introduced a unified data efficient framework that jointly leverages representation learning and principled uncertainty estimation to achieve reliable OOD detection in Earth observation. Now, the dataset and the methodology part. To rigorously test this, we set up a specific dataset pipeline. First, we use BigArtNet S2 for unlabeled pre-training. Then we use Eurosat as our in-distribution target dataset for fine-tuning. Finally, we use UCMERGed as out of the distribution benchmark for testing. Our framework is called Contrast Then Confidence, and it operates in three distinct stages. Stage 1 is contrastive pre-training. Here we perform SimCLS-style self-supervised learning on about 270,000 unlabeled BigArtNet S2 images. We can see the high-level overview of the contrast then confidence C-square framework here. Stage 1 is contrastive pre-training. Uh, as you can see in the detailed diagram, we take an original satellite image, generate two augmented views, and pass them through a shared encoder to maximize their similarity using the NT-gent loss. Critically, we didn't just test one architecture, we evaluated this using a custom lightweight CNN, a standard ResNet 50, and Vision Transformer, which is the B16, to understand how architectural choices impact the pipeline. Now the second stage, supervised fine-tuning. We take those pretend encoder and attach a dropout regularized classifier and fine-tune them on the Eurosat dataset. To preserve the representation we just learned, we use a progressive unfreezing strategy with discriminative learning rates. Stage 3. Uncertainty-aware O detection. This is where the confidence part comes in. During inference on our test set, we don't just do a single forward pass. We use Monte Carlo dropout, performing 50 stochastic passes per image. This allows us to make a map a distribution of predictions and extract true epistemic uncertainty, that meaning the model's uncertainty about the data it hasn't seen. Now we'll talk about the result. the architecture, and the pre-training results. Let's look at the results. We measured performance using AOC rock, area under the precision recall curve, AUPR, and the false positive rate at 95% true positive rate. Our first major set of findings revolves around the role of architecture and pre-training. We found that the effectiveness of self-supervised contrastive pre-training is strictly architecture dependent. It's not a silver bullet for every model. So, if you look at the table, specifically the vision transformer rows, when trained from scratch, the VIT performs fairly, essentially falling to to optimize. But under our C-square contrastive retaining regime, it bridges the optimization gap, wielding a massive gains. Accuracy jumps by over 40% and its O detection AOC rock jumps by 0.27 and reaching a strong 0.8725. For WITs, pre-training is absolutely essential. However, the story flips for convolutional models. If you look at the top rows for the custom CNN, pre-training actually degrades both classification accuracy and OOD detection compared to training from scratch. Because CNN already have strong spatial interaction biases, forcing them through this specific retraining pipeline wasn't helpful. In fact, our custom lightweight CNN trained entirely from scratch achieved the highest absolute OOD detection score on the board at 0.9255 EU rock. This tells us that if you were deploying a lightweight CNN, you might not need massive pre-training budgets for robust O detection, but if you use a transformer, you absolutely do. Now, we'll talk about the uncertainty and OOD scoring results. Our second major findings addresses how we measure confidence. Currently, the standard in most deployed systems is to use deterministic confidence, specifically maximum softmax probability or MSP. We can see the far left plot, that is MSP. If you look at the first plot here showing the MSP distribution, the blue bars are our in distribution Euroset images, and the red bars are our OOD USIMERS images. As you can see, they are completely overlapping. Both are clustered at the far right. The model is highly confident about both. MSP behaves almost randomly under OOD condition, making it incredibly dangerous for real-world deployment. Single forward pass confidence scores simply cannot capture epistemic uncertainty under domain shift. Now the third plot, mutual information. But look what happens when we switch to Bayesian inference via Monte Carlo dropout. The third plot shows mutual information derived from those 50 stochastic passes. Here, the red and blue distribution begin to cleanly separate. The model successfully recognized that it is uncertain about the OOD data. Across all architectures and regimes, Monte Carlo dropout consistently improves OOD separation, and among the probabilistic metrics we tested, including predictive entropy and variance, mutual information, was consistently the superior and the most reliable metric for separating familiar and unfamiliar data. Now, the conclusion and the wrap up of our paper summary. So, to summarize, reliable OOD detection in Earth observation doesn't come from just applying the newest model or a single technique. It emerges from the precise interaction of model architecture, transfer learning strategy, and uncertainty modeling. If there are two things to take away from our work today, it is this: first, architecture matters, Viewed disparately, it needs pre-training to be robust, while CNN can perform exceptionally well from scratch. Second, standard deterministic confidence measures like MSP will confidently you when fail you when the data shifts. Moving to a Bayesian inference approach like Monte Carlo dropout using mutual information is not just a marginal improvement, it's absolutely essential for safe Earth observation deployment. Thank you so much for your time and attention.